Good morning, everyone. Questions? Do you have any questions from the homework?
Hi there. I don't have the classroom camera up today because there's only one other person in here right now.
Yeah. That makes sense. I was expecting that.
Yeah.
Yeah.
Uh, if
Yeah.
if
So
anyone else comes in, I might put it up. But
yeah. I was expecting this. Thanks, Arthur.
uh,
Questions from the chat. Sorry, any questions from the homework? As usual, you can put them on chat before we start. Could you cover H? Okay, we can do number H. All right. So that's H from the homework. We have to evaluate the integral from 0 to 1 of cosine 3x minus 3 dx. Okay. So question number 1, do we need a substitution in this problem? Yes or no? Quickly. Do we need a substitution? Absolutely. The minute we have an inside function, substitution is in order. And 3x minus 3 is the natural substitution because its derivative is a constant, so we don't have issue with that. So my du is the derivative of 3x is 3 times dx. Now we can, as I said yesterday, change the limit as the beginning. So we're going to do that, change limit. If x is 0, u is minus 3, x is 1, u is equal to 0. And now everything verbatim in terms of u. So this would become the following. The 0 is minus 3. The 1 went to 0. Cosine of u. And the dx is 1/3 du. So now I have a fairly simple integral in u. I don't care about x anymore. X is gone. So now I will have 1/3. That's my constant. I can pull it out. Antiderivative of of cosine is sine, evaluated between minus 3 and 0. So no more x anymore. That's my new integral. Everything is done. So finally, I will end up with 1/3 sine 0 minus the sine of minus 3 is equal to 1/3. The sine of 0, I expect you to know that. That's a 0. Now, sine of minus 3, of course, you don't know what the sine of minus 3 is, so you just keep it. But what we should, it's nice to know that the sine of minus an angle, so minus theta, is actually minus the sine of theta. So sine of minus 3 is minus the sine of 3. That's use the definition of the sine. So this would give me minus minus plus sine 3. And finally, we get 1/3 sine 3. Remember, that's a constant. There is no c's in it. There is nothing. That's really the answer. Okay. Any more questions? All right. So today we are going to start basically the new material. So I will start with section 6.2. Basically, it's an easy section. It's just prepare us a little bit to the next few sections. So it's a very good, it's an easy section to prepare us for the way of thinking for what's coming up. So section 6.2, area between two curves. So let us recall exactly what we have. Recall what we know so far about area. So let us recall that if a function is positive on an interval AB, positive is absolutely important then, so this is my function. My function is positive, then the area under the graph, so the area of this region is basically the Riemann sum when the number of subdivisions very large. So it's the integral from a to b of f of x dx. So that's exactly what we know. Now the question we're gonna really look at today is the following. You don't have to write, just let us listen a little bit before you guys write anything. Suppose I have the following scenario. Again, my scenario is simple. And I have a function f right here and g. So this is the top function if you want, and that's the lower function. This is a and b. And I'm interested in the area between the two curves. Okay, so intuitively, based on this main idea, what's going to be the area in this case? Because I said you don't have to write because we're going to do this problem again. But now I want to ask you a question. So what do you think the area is going to be?
Is it going to be f of x minus g of x?
Be very precise. What do you mean by f of x minus g of x?
So the big area, like the top curve. So if you just take the derivative of that, or the integral,
Right.
and if you subtract it by the area of g of
Right.
x.
So it's the integral of f. That's purely geometric. So that's the area under the big curve. And as your classmate rightfully said, you take away the area under this one. So minus the area under the little curve. So in this simple scenario, the geometry is not very hard. So another way to write this, if you want, is the integral from a to b of f minus g. You can combine them because you have exact same limit. Okay, so this scenario is easy. Now, suppose I'm going to take fairly similar problems. I'm going to change the picture a little bit. And this is the picture now. Okay, so suppose I have, this is a function f. That's really the top curve right here. And the bottom curve, I'm going to start wiggling it a little bit. This is my A, and this is my B. And this is my function g of x. Okay, so what's going to be the area between them? Is this scenario harder than the previous scenario?
Yes,
Because,
because we're including the negative of g of x.
right, we're looking the negative of g of x. So here it was clear cut. I have no issue. Because g is positive, the integral from a to b of g is going to be the area which is outlined in red. However, in this case, the problem definitely become hard because the integral of from a to b of g of x is plus this area, minus this area, plus this area. So it's complicated. So the question is, how can we find the area? Are you with me so far? All right. So again, before I start doing this and you realize it's not going to be hard, I have to talk a little bit about vertical distance between 2 points. So vertical distance between 2 points. Vertical distance between 2 points. So let us say I have a line, that's a vertical line, usually it's going to be the y-axis, and this is the 0 of the y-axis, and I have 2 points here. I'm going to call them C, and I'm going to call this D. Okay. And my simple question is, what's the length from here to here? What's this length in terms of D of C? Very quickly, it's a simple question. What's the length from here to here? So
Is it D minus
what?
C? D minus C?
D minus C. Because D is from here to here. That's your D. You're taking away the C. What you're left with is the length from here to here. So it's very there. Now, let us see a second scenario. So suppose my 0 is here, my C is down here, and my D is here. I changed the scenario. It means I'm letting 0 to be in between. And my question is the same. What is the length from here to here? Anyone?
Could you possibly say it's D plus C since C is inherently negative? It's just both those distances combined.
Okay, I'm going to write it in pencil. D plus, so D will give me from here to here, right? What do you want to add to it?
C.
If I add C to it, do you think it's correct? Let us say D is 4. C is minus 2. If I add D to C, I get 4 minus 2, which is going to give me 2. Obviously, the distance is not 2. Absolute value of C is correct. Absolute value of C is correct. But what is the absolute value of C in terms of C? If I do not want to put the absolute value of C, what can I write exactly? Plus the minus of C. Is that correct? The minus of C. C is negative. What you're going to add to it, not C, you need the minus the C. So if C is minus 2, you need to add the minus of minus 2. So you get the exact length from here to here. So this is a D here. And from here to here is actually minus C. That's the length of it. So this length is also D minus C. So if you have 2 points on the vertical line, regardless where 0 is, the distance between them is going to be always the upper value or the upper value. You take away the smallest value, regardless what C is. Whether C is above the x-axis or C below the x-axis, it doesn't really matter. So the distance is always, so the length is always, you take the upper value, whatever it is, minus the lower value, whatever it is. So in my scenario right here, the length is going to be, so if I let D to be 4 and I let C to be minus 2, and according to my formula, the length is 4 minus 2, which is equal to 6. You guys understand why I can put minus C in here? Okay, so whenever I have 2 points on a vertical line, the distance between them is always the upper value minus the lower, regardless where the points are located on the vertical line. Now I'm going to go back to my problem of area between two curves. And this idea here, we will be using it a lot in this chapter. So area between two curves. Two curves. So let's see what my problem is. So we're going to call R, let R be the region. Let R be the region. Bounded from above or from the top, from above by the graph of f of x. So the top I have f of x, below by y equal g of x, and the lines x equal to A, and x equal to B. The question is, find the area. That's our goal. Find the area of the region R. Okay, so this is the picture. Let's see how we read this verbatim. So how do we read that? R is the region bounded from the top by y equal f of x. This is f of x. That's the top curve. From the bottom by y equal g of x. And I didn't say anything is positive. Nothing is necessarily positive here, but we know what the top and we know what the bottom here. That's g of x. The line x equal to A. This is A. That's the line x equal to A. So I have to start from here. And the line x equal to B. This is my B right there. And the region in question is this one. And the question is, find the region. All right, so we had some difficulties because as you guys said, you know, the G is negative, positive. So we had difficulty just using the pure geometry to do this problem. So what is going to be our approach? Our approach is like this. Whenever we have something, a physical quantity, we have to evaluate. And we have hard time doing it. The way we are going to do it is by approximating it by things we know how to compute. So the idea is that I'm going to take this region and again, fill it up with rectangle, tiny rectangle. Find the area of each rectangle and add them. And that will be the way we will do a lot of our problems in this chapter. We're going to take something, we're going to approximate it with what we know, evaluate what we know, and then add them up. So I'm going to cover this region by rectangle, tiny rectangle, evaluate the area of every one of them, add them, and then we come up with the formula that we need. So let us see what I am going to do. So I will draw two pictures. One just to tell you the idea, and one I will work with. So this is my F again. Try to make it the same thing. And this is my G again. And this is my A, and this is my B. Okay. How I'm going to approximate it with rectangle. So in this picture, I will show you the approximating rectangle. The way we're going to do is we take the interval from A to B, and we're going to split it into pieces. So now I will not take a lot of them. I will take few pieces. And then these are the rectangle I will fill the region with. I take this piece here, which is going to be x1, and I take the following rectangle. The rectangle whose height starts from the bottom curve right here all the way to the top curve right there. And this piece here, so we're going to split the interval like we did before, and this will be the width of my rectangle. So that's going to be rectangle number 1. Rectangle number 2 will be the same. I will be calling this x2. And the rectangle goes like this. The length starts from the bottom all the way to the top. And that's going to be the width of my rectangle. So that's the second rectangle if you want. And I will keep covering the whole region with those. So my last rectangle is going to be this one. And so from the bottom to the top. And this would be my delta x from here to here. So these are the rectangle, approximating rectangle. And now I will find the area of every one of them. So I think the picture is clear from the bottom to the top. This is what I will be doing again and again. Bottom to top. Bottom to top. Now we are going to find the area of every one of them. Each one of them. I will focus first on the first one, and then I will do an arbitrary one that we are going to call the typical rectangle. So let me focus on the first one because to help us. What's the area of this piece right there? So I call this point x1. What's going to be the area of this piece? So I'm dividing AB. So that's the idea. We divide AB into n equal subinterval. And we call delta x the length of every one of them. Now my focus is this rectangle. What's the area of this rectangle? To find the area of this rectangle, I need the length from here to here, and I need the width. The width is easy. The width is my little delta x. But what's the length of this triangle, of this rectangle? How much do we have from here to here? Let's think a little bit. This is y equal f of x. We're gonna call it the upper curve. This is g of x. We're gonna call it the lower curve. My question to you is, what's the length from here all the way to here? Can anybody? F of x minus g of x? Is your classmate correct? And let's see why. If this is x1, it means this point here is x1 f of x1. It means this point here is the value of the function at x1. This point down here, this is the curve y equal g of x. So if this is x1, this point here is g of x1. So the distance from here to here, I don't care whether g of x1 is positive or negative, but based on the comment we did a minute ago, this vertical distance is f of x1 minus g of x1. So the area of the first rectangle is going to be the length f of x1 minus g of x1 times the delta x. Questions before I proceed? What about the second rectangle? What is going to be? If I call this point x2, the length is going to be f of x2 minus g of x2 times the delta x. The same thing for this rectangle and that rectangle and that rectangle and that rectangle. So the way we do this problem is, that's the idea. We say instead of finding the area of the first, then the area of the second, what we're going to be talking about is something called typical rectangle. And what do I mean by typical rectangle? Again, I draw the same picture right here. The same thing, I'm not changing. This is my B and this is my A. And we're going to divide this into pieces. But now, instead of focusing on the first by itself, the second by itself, the third by itself, I take one of them, which I call a typical one. It means a rectangle that represents all the pictures. So I will call this xi, and this is the one before it, xi minus 1. And I call this rectangle a typical rectangle. It means a rectangle that represents a generic one, the one that represents every one of them. So the way we will approach this problem is, instead of taking a lot of subdivision, we focus on one. So that's my typical rectangle. So this point here, this is xi, f of xi. And this is xi, g of xi. Now, what's the area of a typical rectangle? What's the area of that? It's the length from here to here times the width from here to here. So instead of telling you what's the first, what's the second, I take a typical one. What's the length? This is xi. This is right here, f of xi. If this is xi, this point here is g of xi. So the length is going to be the upper value minus the lower value. And the width is going to be delta x. So I'm going to analyze here a typical rectangle. Every typical one, the length is going to be f of xi minus g of xi. The width is going to be the delta x. And finally, the area of every typical rectangle is going to be the length times the width. The length times the width. That means every one of them, I know the area of the rectangle. Now, what's the sum of the area of the approximating rectangle? That means if I take those rectangles, those what I call approximating, what's the sum of their area? So the sum of their area is f of x1 minus g of x1 times delta x plus, etc. f of xn minus g of xn times delta x. It means the sum of the area of those rectangles is the following sum. Sigma I equal 1 to n of f of xi minus g of xi times delta x. Now, have you seen anything like this before? Have we seen,
Yes.
what does this sum look like?
This looks like just a regular like Riemann sum, but just
Exactly, that's a Riemann sum. Crucial. But that's really look like a Riemann sum, where the function is in question is this one here. That's the function in question. So the approximating rectangle, their sum is exactly that. So what's the area now of the whole region? Quickly, what's the area of the whole region? So the area of the whole region is what happened to those sums when what? What do you think I'm going to write here?
When they approach infinity?
Right. When the number of subdivision approaches infinity. So the area of R is going to be this limit when n approaches infinity. But now by the definition of definite integral, by the definition of definite integral, what we have? The sum is the following. Now I'm using the definition. It looks exactly like the integral. This is the function in question right there. F of x minus g of x dx. So it's the same formula we had geometrically. And now what are the upper and the lower limit? We think as follows. We said to be able to cover the region. That's how we're going to find the limit. To be able to cover the region with those approximating rectangle, which interval we have to divide into pieces. We have to divide the interval from A to B to be able to cover. So the limit of integration is going to be the integral from A to B of f of x gx. Okay. So that's how we're going to find the area, because we knew we had issue. My function is positive, negative, so that's going to be the area. So now we have the following idea. So if R is the region bounded by y equal f of x, U stands for upper. If you guys are writing, the U will stand for upper curve. The lower curve, g of x equal to A, x equal to B. Then the area of R is going to be the following. The integral from A to B of f of x minus g of x dx. F is always your upper curve, because we're finding the length of those approximating rectangle, and g would be your lower curve. Because remember, the f of x minus g of x represent the length of the rectangle. The dx is representing the width of every rectangle. Okay. So I think I have to start the quiz now. I will assign like 2 or 3 problems, and on Tuesday we solve a lot of problems relating to this idea, just to give you how I am expecting you to do those problems. So basically, my expectation for us to do those problems is as follows. We draw the region. We draw a typical rectangle. That's how we're going to approach this. Once we draw a typical rectangle, we find its length, its width, its area. We write the sum, and then we move to the integral. So even when we're doing simple problem, we will go through the same process again till the process become part of us. Right? Okay, so now time for the quiz. Do you guys have bright space in front of you? Any question before I start?
I'll pull it up. Hang on.
Okay. So get bright space and go to activities in bright space. From the activity, go to assignment. And you will see your quiz. Click on it. The quiz will be there. You take it and then you upload it. And I will be staying with you. So you guys, you can always ask me any questions, because I'm with you all during this time. You can, of course, use chat to ask me questions, and privately. Okay. Did you guys find it?
I found it. I just wanted to ask, do I have to write out the questions or can I just write?
No, just say the number.
All right. Thank you.
Just
Appreciate
write
it.
the number, put them in order, and write it clearly. That's really
Okay.
all I want. And PDF, because otherwise, Brightspace does not read anything you guys give me. PDF is the most safe one for me to read.
Okay. Awesome sauce. Thank you.
Okay. Any other questions? Okay, I'm gonna mute myself, but you guys, I am with you here.
It'd be a bit difficult to show my work because I'm gonna be like typing this on here, but I'm sure I can make this work. I've done this kind of thing before on like whatever it's called.
Arthur, do it clearly on a piece of paper.
I do not have paper. Do you have paper over there? Yeah, and then I also need a pen.
Okay?
Yeah, that's no worries. I got a pencil now. All right. Oh, I got the paper, so I'll do it on there.